Alright, well, welcome to hydraulic engineering. I hope you're doing well. Let's go over some announcements here, and then we're going to work through a couple of examples that tie into the homework that you've got due on Friday. That's the first of the announcements. Is homework number 9 is due on Friday, and that includes a problem having to deal with a bed step and a bed drop. And we had several classes that were devoted to using the specific energy equation to find what's going to be the new depth downstream when the water flows down off of a drop-off, or when the water is flowing up over a step. In fact, I think that was the topic of one of our last class meetings before we went virtual, and also one of our meetings when we did go virtual. We were kind of reviewing that. So there's one problem with bed step drop. There's one problem with the maximum elevation of an obstruction that can be tolerated, and that's kind of what the examples on Monday were meant to address. And then there's one problem having to do with channel expansion. And the channel expansion problem we're going to go through today in the examples that we work. And so that assignment is due on Friday. And then Monday of next week is when you should submit your reservoir sizing. In class on Friday, I'll show you how to do the reservoir sizing. If you haven't started it yet, that's okay. And this is going to be one of the rare occasions when I'm not encouraging procrastination, but it's not going to be an issue because phase 3 is pretty quick. You don't have to do the cost analysis for that phase. That phase just is exclusively limited to sizing of the reservoir. And with Microsoft Excel, you can get it done pretty quickly. So I'll show you how to do that on Friday, and then you'll submit your reservoir sizing on Monday. Now, just on the subject of the project, I've started grading the first couple of maps so far already. I've given feedback on those. For the most part, they're looking pretty good, and I hope to continue making the suggestions. Now remember, there's a final submission for the project, and it's in that final submission where you include your revised demand estimation, your revised network design for the maps. And so, like in phase 3, you're sizing the reservoir, but you don't have to make any changes to your network maps for phase 3. Even if you've made adjustments to the network maps, I'd rather not see them until the very end, unless you want to make an appointment to go over it with me. But the point is, you don't need to submit that during phase 3 where you're just focusing on the reservoir sizing. Okay, the other announcement, exam 2 is going to be on Wednesday, so a week from today we'll have an exam that I email to you. You'll upload it to Blackboard when you're done. We'll talk more about the format of the exam as it gets closer, but it's going to essentially be kind of an open book, open notes test where you've got an extended period of time available to take the test. Alright, so before we start talking about expansions and contractions, do you have any questions related to the announcements? If there are none, then we'll go ahead and get right into it. All right. Water is flowing through a channel, and oftentimes, especially in natural channels, the width of the channel is going to be occasionally changing. It may contract, it may expand, but let's first focus on the case of what happens from a specific energy perspective when the channel is getting narrower. So remember that B stands for the width of a channel, and in this case, just for simplicity, let's assume that it's a rectangular channel, and so lowercase b is what we usually use to describe the bottom width of a channel. So at location 1, there's a certain bottom width, and if we know the flow rate that's going through the channel Q, then we can also calculate the flow per unit width. And so the lowercase q that's shown there on the screen is the large Q, the flow rate, divided by the flow per unit width. So there's the formula there, flow per unit width. And then at location 2 downstream, after the channel got a little bit narrower, it's going to have a different flow per unit width. Even though the Q at 1, the big Q, uppercase Q, the flow rate is the same at location 1 and location 2. Since the channel is narrower, now we have a greater flow per unit width. Because if you look at the formula for lowercase q, you're dividing by b in both cases. And so if b is less, then that means the flow per unit width is more. So now think about the critical depth formula. It's shown on the screen there. Critical depth for a rectangular channel, remember this equation, this shortcut equation that you're seeing for the critical depth in terms of flow per unit width, lowercase q, that's only valid for a rectangular channel. If you had trapezoidal or any other shape, you'd have to solve for the critical depth the long way, which is to say by assuming that the Froude number is 1 and solving for the depth when the Froude number is equal to 1. But here we have this shortcut. So what happens when the channel gets narrower? How is that changing the critical depth? If we look at the specific energy diagram, what it shows is one specific energy diagram curve for the first case when the channel was wide, and another specific energy diagram curve for when the channel got narrower. Now remember, the flow rate, large Q, is the same at 1 and 2. But what's different is that the channel width is narrower at location 2. So what that does is it shifts the specific energy diagram. It shifts it to the right and it shifts it upward. So Q1 is the curve on the left, lowercase q1, corresponds to the specific energy diagram curve on the left, and lowercase q2 is the specific energy diagram curve on the right. So think for a moment, why did it shift the curve? It's shifting the curve because on the one hand, the critical depth is larger when B is smaller. So just look at the formula that's on the screen there for y sub c. If B gets smaller, then lowercase q is bigger. If lowercase q is larger, then y sub c is larger. So you have different critical depths depending on how wide the channel is. A narrow channel has a taller critical depth. And since minimum specific energy, the shortcut that we have for a rectangular channel is that the minimum specific energy is 3/2 the critical depth. So up at the top left side of the screen where I have, it says remember. It's just kind of a shortcut that you can keep in mind that when the conditions are critical, the depth is 2/3 of the specific energy and the velocity head is 1/3 of the available specific energy. So if you want to calculate how much specific energy is there when you have critical flow, you just multiply the depth by 1.5. So any questions so far about these concepts or the fundamentals of what happens when the channel is getting narrower? The key takeaway that you need to remember is the specific energy diagram is getting taller and it's shifting to the right. Because the reason why that's important is it tells us what the new depth is going to do. We can we can solve it numerically and find what's the new depth, but we could also solve it graphically. What this is showing is that if you had subcritical conditions at 1, then the channel gets narrower, then the y2 depth is going to be less. And this is really counterintuitive. Think about it. What we're saying is that if the channel gets narrower, the flow depth is decreasing. And I bet most of you, if I'd given you a guess, if I'd said, hey, just speculate for a minute. Speculate. Do you think if the channel gets narrower, is that going to make the water deeper or shallower? I think most of us would look at this constriction where the flow is contracting and we'd say, well, I guess since the channel is getting narrower, that must mean that it has to also be getting deeper. But we'd be wrong. If conditions are subcritical, what the specific energy diagram analysis tells us is that actually the depth downstream, the depth at location 2, is going to decrease as a result of this change. So we're going to put that to the test. We're going to work an example today where we look at a contracting channel and we'll calculate the new depth with a specific energy diagram. So this is a contraction. We can do the same kind of thing with an expansion. Before we look at the case of the expansion, I wanted to remind you of that there's several different ways to see the specific energy equation. The specific energy equation in concept is that at two locations specific energy is conserved. So if the energy at 1 is known, you can calculate the conditions at 2 by setting the two specific energy at both locations equal to each other. And the two terms of specific energy are the depth term and the velocity head term. We don't have the z term here because we're not talking about total energy, we're talking about specific energy. And specific energy is measured above the bottom of the channel. So of course, between location 1 and location 2, the water is flowing downhill. And by definition, we assume that 1 is the uphill location and 2 is the downstream location. But we're not accounting for the elevation change. We're just looking at how the specific energy is equating between the two locations. And so we can write that equation in terms of the velocity head with V1 and V2. Or if we don't know the velocities, but we do know the flow rate, Q, you can see the equation in the middle there is writing the velocity head in terms of Q squared divided by 2GA squared. So that's another way you've seen the velocity head expressed. And at the bottom is maybe the most obscure way yet of expressing the velocity head term. And I think that this is one of the ways that we looked at it on Monday. It's the depth, y1, plus flow per unit width, so that's the lowercase q, is large Q divided by B. That's flow per unit width. So flow per unit width squared divided by 2g, and instead of a squared, we substitute in the depth, so y1 squared. So this is another way of writing the specific energy equation. We've got three options to choose from when we're doing a specific energy analysis. Just wanted to remind you of that. So here's the case of the expansion. We talked about contraction earlier. Expansion is similar. You have a flow per unit width at 1 and a different flow per unit width at 2, because if the channel is getting bigger, if B is increasing, that means now you're dividing uppercase Q by a larger number, so Q2 will be less. So think conceptually, what is that going to do to the specific energy diagram? In the first case where we had a contracting channel, it pushed the diagram to the right and upward when the channel expanded. So what's going to happen instead is the channel expanding is going to push the specific energy diagram to the left and downward in the case of an expansion. And so think about why that would be in terms of the critical depth. So at 2, the critical depth is lower, so y sub c at location 2 is less. And so if y sub c is less, then that means that the minimum specific energy, E min, is less, because E min is 3/2 times y sub c. So it shifts the curve lower and to the left. And we could use a graphical approach to find out what's the new flow depth. All right. Sometimes we account for energy losses during a transition like this. In this version of the energy equation, this is assuming that there's no energy loss in the transition. But sometimes we do want to account for it, and when we want to account for it, you'll notice that it's on the right-hand side of the equation. So this is really similar to what we've seen in the past with the energy equation when we were applying it to pipes. Remember where the H sub F term would be on the right side of the equation, where location 1 is upstream, location 2 is downstream, so that means the water is always flowing from 1 towards 2. So what this is saying is there's some loss coefficient that's proportional to the amount of energy that's being lost when you multiply it by the velocity head. So we're saying that the energy that's left over at 2 is how much energy there was at 1 minus a loss term, which is this coefficient that would be given in the problem statement multiplied by the velocity head. Okay, so any questions so far about the concepts that we've been discussing? Any questions about the concepts having to do with specific energy and what happens when the channel gets wider or what happens when the channel gets narrower? Okay, let's then move to a specific example. Let's look at an expansion where the flow rate is it's steady. It's not changing over time, so the big Q, 9.9 cubic meters per second, that applies at location 1 and at location 2. That's our known flow rate, but the channel is expanding. So the width of the channel at location 1 is 3 meters. We know the flow depth there, and we know this coefficient, which is having to do with how much energy is going to be lost through the transition. What if the channel expands from the first width of 3 meters to a new width of 5.7 meters? So the channel's getting wider. We want to find out what's the Y2 depth. So we're going to solve the specific energy equation to do that. So here's the specific energy equation, the one that is accounting with the effects of energy loss included. So what do we know so far? We know Y1, that's given. We can calculate Q1, meaning the flow per unit width at 1. We can calculate that. We can calculate Q2, lowercase q2, because we know uppercase Q and we know the width at location 2. The only thing we don't know in this specific energy equation is Y2, the unknown depth downstream. So here's the process, and I'm actually going to pause, and instead of just showing you the solution to this one, I'm going to ask that you take a piece of scratch paper or there in your notes, go through the steps that are listed A through F. First of all, calculate what is the flow per unit width at location 1. Part B, calculate the critical depth at location 1. And so you can use the formula for Y sub C that's shown on the screen there. So you calculate the critical depth at 1, and then in part C, you are determining the flow regime. Remember, we want to find out if it's supercritical or subcritical, because that's what tells us which of the routes to select when we do finally solve the specific energy equation. When we solve these cubic equations, like the specific energy equation, there's going to be a negative root, and then there's going to be a small value for Y2 that corresponds to what if conditions were supercritical. And there's going to be a large value for Y2 that corresponds to what if the flow conditions are subcritical. And you don't know which of those two non-negative routes to select until you've gone through the process of determining the flow regime at location 1. So that's what step C is all about, is determine, do we have super or subcritical at location 1. So then in part D, you calculate the flow per unit width at location 2, and then you substitute all of those knowns here in step E. You put everything into the energy equation and solve for Y2. All right, so I'm going to pause for a moment. I'm going to quit talking so that you can actually start crunching the numbers. This is when I would start circulating around the room and hovering over your shoulder to see what your calculations look like. But if you have any questions, you can type it into the chat box there, and I'll answer your question by chat while I'm being quiet and giving you some time to start crunching the numbers. And then of course I'll pull up the solution in a few minutes so that we all see if it makes sense. All right, well, if you're totally stuck, I don't want to continue making you to wait. The suspense is probably killing you. So let's see, we're doing the expansion example. Let's take a look at the process here. The instruction said that the first thing you needed to do is calculate the flow per unit width at location 1. So lowercase q1. So here's the flow per unit width at location 1. We have 9.9 cubic meters per second, and we're dividing it by a channel width of 3 meters, then that gives us 3.3 meters squared per second. So the units there, if you think about it, that's a flux. It's talking about how many cubic meters per second are flowing through each meter width of the channel. So we could say either how many cubic meters per second per meter width there is, so we could say cubic meters per second per meter, or just canceling out the like units makes it 3.3 meters squared per second. All right, the step-by-step also said that we need to compare that to the critical depth at 1. So let's calculate the critical depth at location 1 using this shortcut that applies for conditions that are rectangular, for rectangular channel. So the critical depth 1.035 meters, and since the given flow depth that is described in the problem statement of 2.75 meters, since 2.75 is greater than the critical depth, then that means flow conditions are subcritical. So when we end up with 3 roots, we're going to pick the root that is the largest, because that would be the subcritical root that we're looking for. All right, so any questions so far on this example where we're just doing the preliminaries here? All right, so step D was calculate the flow per unit width at location 2. So that is 1.737 meters squared per second. So that's the flow per unit width downstream. And from that we can now substitute into the energy equation. So this is the specific energy equation that says that the depth plus the velocity head at 1 is equal to the depth, velocity head, and losses at 2. So in other words, the specific energy at 2 is going to be less than the specific energy at 1 in the amount of the losses that occur. So if we put all of the knowns for this, the depth at 1, flow per unit width, the flow per unit width at 2, the C factor, that coefficient for this expansion of 0.45, the only unknown that we have in the equation is the depth, y2. So we rearrange that a little bit, do some algebra. On the left-hand side, 2.823 meters. On the right-hand side, we've got y2 and then some numerical factor divided by y2 squared. And for it to be a cubic equation, we have to multiply all of these terms by y2 squared. And then I've done that and rearranged the equation. So we've got y2 cubed minus 2.823 y2 squared plus our leftover constant 0.223. And you can pop that into the weak and sickly Casio calculator and solve for the 3 roots. We've got the negative root, the supercritical root, and the subcritical root. And of the 3, we pick the subcritical root because the conditions at upstream were subcritical. You know, we had the given flow depth was greater than the critical depth. We could have also calculated the Froude number at 1. If you're more into that, you could calculate the Froude number at 1 and know whether it's super or sub. In any case, since it was subcritical upstream, it will remain subcritical downstream, and that tells us that we pick the larger of those 2 positive roots. So choose the subcritical depth. All right, so what do you think? Pretty good stuff, right? Did that example seem more natural than what we did on Monday? I hope so. I hope we're all adapting. Any questions about this one before we continue forward? This was the example of what we do when the conditions are expanding and when we are accounting for a loss. In the next example we look at, we're going to neglect the loss, but this time we included the effect of that expansion coefficient. So any questions before we move on? All right. Well, what if the opposite happens? Instead of expanding, what if it contracts? Oh, by the way, how did this correspond to what we were expecting? You know, like the new depth? The new depth, it says 2.79. So what was the original depth? The original depth was 2.75. So it got wider and it got deeper, but remember this loss also occurred. So sometimes that throws a bit of an unknown, a curveball, where you could have maybe reasoned through it with the help of a specific energy diagram if you didn't have to account for the loss. But it ends up that it's getting wider and it's getting a little bit deeper, where maybe we would have thought, well, if it's getting wider, that must mean it's going to have to be shallower. But no, it's getting wider and deeper. So how is that even possible? If the flow rate, if the lowercase q is, no, I'm sorry, if the big Q is the same, you know, if the flow rate in and out is the same, how is it possible that it both got wider and deeper? How does that not violate the continuity equation, which cannot be violated? There is an answer to this. Anybody realize what's happening? How is it possible that in equals out if the water got deeper and the channel is wider downstream at location 2? Downstream is moving slower. James got it. That's exactly right. The velocity decreased. So it's not necessarily that the water is stalling. It's just Q is V times A, right? And so the A is flow depth times the width of the channel. That's the cross-sectional area. But the other part of the flow rate, Q, is the velocity. So the velocity, when the channel got wider, that causes the flow velocity to decrease. And in this case, it's decreasing considerably because that channel got a lot wider and it got a little bit deeper. So the velocity decreased. That doesn't mean that Q in and Q out don't equal. They do. This is still equilibrium. It's still steady flow. It's just the velocity downstream is less. Good job, James. You get a gold star. All right, so any questions before we take a look at this example with a rectangular channel that is now contracting? Okay, so similar process to before, except for this time we're neglecting the effect of the transition. In other words, we're not accounting for a loss. The C value doesn't need to be thrown in there. So we know the width of the channel, the depth of the flow, and we're given the flow velocity is 3 feet per second for this one. And what we want to know is how narrow can we make it and avoid choking. Now the hint, you know, what does that mean, avoid choking? That means assume that the flow depth at 2 is equal to the critical depth. Because like the critical depth is the last possible depth that you can have before there's not enough energy and choking occurs. Remember that on Monday, choking occurred when the obstruction height was too big, and when the water didn't have enough energy to flow over that obstruction, it had to get deeper upstream. So here, what we're doing, instead of having a big block in the channel, instead of the obstruction being vertical, we're contracting the channel, and that potentially could obstruct the flow. So we're asking, how narrow can we make B and still get the water through that channel without any disequilibrium, without causing choking and pooling upstream? So the hint on what to solve for when we substitute it into the energy equation is, first of all, you'll calculate E1. So E1 is going to be depth and velocity head at 1. And now we're assuming that E1 and E2 are equal because we're neglecting the losses, and we are able to calculate the critical depth as 2/3 of the minimum specific energy. So in other words, you're going to solve for YC using that 2/3 relationship, which is kind of the inverse of what I said before. You know, if E min is 3/2 of the critical depth, then that means the critical depth is 2/3 of E min. So this time, we know how much specific energy is available, and we're calculating the critical depth to be 2/3 of it. And then finally, once you've done steps A and B, then we've got enough information about what's going on downstream at location 2. We know the flow depth. Then we can calculate, if you know B, excuse me, not B, you're going to know the depth and you know the flow rate, so then you can calculate what velocity it has to be, and if you know the velocity, you can calculate the area, and then if you know the area, you can calculate the width. Alright, so C maybe is going to be a little bit tricky to visualize all up front, but I'm going to pause again and give you some time to calculate the E1, so that's how much specific energy there is at location 1, and then find out what's the critical depth that the water is flowing at using this 2/3 relationship that's shown on the screen. Alright, so Jeffrey, yes, you have the correct E1, and the Y sub C, though, is not correct. Alright, Josh has got it up to this point. Thank you. Let me show you, Adam's got it. Josh, yes, that's the correct Y sub C. You are correct, sir. You win the gold star. Let me pull up the solution just to go over this. Contraction. You found the actual gold star. Well done. You get a gold star. Alright. Alright, so here's the contraction. Okay, so you can see that E1, the amount of specific energy at location 1, is going to be the depth and the velocity head. So we have to be mindful of the fact that we're working with traditional units here, so G isn't going to be our normal 9.81 because we need it in terms of feet per second squared. So it's 32.2 is what we have for the G2, for the G. So that means that there's 5.14 feet of specific energy upstream. And so if we're making B so small that it's right on the verge of choking, that means that's going to force critical flow at location 2. That narrowest channel that can accommodate the flow, the water has to be as efficient as possible, and critical flow conditions are the most hydraulically efficient way to get water through some obstruction. So we're making the channel so narrow the water doesn't have any choice but to flow at critical conditions. So we assume that since we've made it so narrow, it's forcing the critical depth at the downstream location, and so Y sub C is 2/3 of that minimum specific energy. So that means that the critical depth is 3.427 feet. Now what about all the rest of this? What about how to find for the velocity, then the area, and finally the width? All we know so far is Q. We can calculate Q because here at location 1 we know the depth, the width, and the velocity. So you can get Q from that, right? Q equals V times A. So what's our cross-sectional area upstream? It's 50 square feet. So if it's 50 square feet and the velocity is 3 feet per second, then the Q is 150 CFS. So that's the flow rate, is 150 CFS because it is the upstream area multiplied by the upstream velocity. So now, what's going on at location 2? If we know that the specific energy is 5.14 feet and the depth is 3.423 feet, then that means that the difference between the two is how much energy there is in the velocity head. So we can calculate the velocity downstream at location 2. Now this is kind of a tricky idea here, but what we're just saying is, remember, when conditions are critical, 2/3 of the energy is as depth, 1/3 of the energy is as velocity head. So our velocity head is a certain amount of feet of energy, and if we know G, what we're doing is we're just solving for V2. So it's a little bit of a workaround, like an adjacent way to find out the downstream velocity is we know that the velocity head is going to be a certain number of feet of specific energy. So if we know V and we know the Q that I was just mentioning, because Q upstream and Q downstream is the same, then that allows us to find what is the cross-sectional area at location 2. So any questions up to this point so far? Okay, so then the last part of it is just, if we know the cross-sectional area and we know the flow depth is 3.427 feet, because that's the critical depth that we solved, it's going to be flowing at that depth, and that means the channel width is 4.17 feet. So let's say that you solved this problem over and over again, like iteratively. You know, if you made the channel width, it started at 10. So what if you went like 10 here and then 9 there? You could find out what's the new depth. Or if you said 10 here and 8 there, you'd find the new depth. So you could keep going and going, but then as soon as you made the channel narrower downstream than 4.17, like if you tried to solve this by saying the upstream depth is 10 and the downstream depth is 4, then you'd get choking. And the way that you know that there's choking is that there wouldn't be enough energy at 1 to give you a combination of velocity head and depth that would also be subcritical downstream. Because conditions at location 1 were subcritical, so they have to stay subcritical. So it would basically be, you wouldn't get an error message, you'd just be looking there at your paper and you'd realize that there isn't enough available energy upstream to make the flow conditions downstream happen. So that would tell you that you had received choked flow. And then you'd have to go through that same process that we did in this example, where we're saying, well, what if the obstruction height is 10 feet and the water itself was 10 feet? Well, if you choke the flow too much, then the water has no response except but getting deeper. And so it's pooling enough energy until finally there's enough energy to force the water through the obstruction, either over the obstruction or force the water through the contraction at some new energy amount. All right. So, any questions about that? All right. Let's take one last look at these announcements. Oh boy, I'm having a heck of a time here. All right. So you've got a homework assignment that's due on Friday. That gives you 47 hours and 12 minutes to finish it. In previous classes, you've seen how to do step and drop. That was Friday the 13th, and then Monday's class we also looked at that, and then the maximum Z that can be tolerated before there's choking. And then today we did a channel expansion type problem. All three of those are the kinds of problems where you're setting the specific energy upstream down to the specific energy downstream, and solving for either an unknown depth or solving for the obstruction that can be tolerated. So if you have questions as you're working on that, feel free to send me an email or give me a call. We can set up a Zoom chat or a Skype chat or a phone call, whatever you need. I'm anxious to make sure that this makes sense to you, and so get in touch if you need help. Have a great day, and I'll see you in class on Friday.